So state variable analysis, this is the second unit, and generally we have two approaches. For analysis. First one is the frequency domain, and second one is the time domain. This is the transfer function approach. For analysis and design of control systems. And second one, this is the state space approach. So this second one is the content of this state variable analysis. In frequency domain analysis, we have few limitations. Limitations are, for this transfer function approach, we can analyze or design systems only for linear invariant, and this is the general approach. In which we can take time varying systems plus initial conditions. For all systems having initial conditions 0 are considered in this approach. And if we have initial conditions for a given system, then we can follow this. So this is the major difference. So we can say this state space analysis is the general method, and before starting state variable analysis, we have few definitions. So general, before starting general state space representation. How can we represent in a general form for a system in a state space? So before starting this, we have few definitions. So you can note down definitions related to state space. Few 4 or 5 basic definitions are there. So first one is the linear combination. What is the linear combination? Linear. If any relation is represented like a1x1 plus a2x2 to anxn, then this type of relation is called the linear combination of n variables. Second one is the definition linear independence. What is linear independence? Suppose we are taking an example like this. Suppose x2 is given by 3x1 plus 4x3. This is a expression which is relating three quantities, x1, x2 and x3. Now all these three expressions x1, x2, x3 are linearly dependent. If we can express any quantity in terms of other two quantities, then this set of three variables are said to be linearly dependent. And if we cannot write any expression in between x1, x2 and x3, then this is linearly independent. Means linearly independent quantities are those in which we cannot express any one in terms of other quantities. So this is the linear independence. Obviously this expression is linearly dependent. So other definitions are also there. So you can note down. Few more definitions are there related to state space analysis. So next is the system variable. What is system variable? System variable. Any variable which responds to input and initial conditions. Any variable which responds, any variable which responds to these two, input and initial conditions, are called system variables. Next one is the state variable. State variables are minimum set of variables these are minimum set of variables in terms of which we can represent all variables of a system. So these are two important definitions, system variable and state variable. So now we are going to next definition. How can we define few other definitions related to state variable analysis? So next one is the state vector. You can note down the definition. A vector whose elements, this is the a vector whose elements are state variables. So this is the state vector. Next one is the state space. So this is the n-dimensional space. This is the n-dimensional space having state variables as axis, n-axis. So this is the state space. So next definition is two more definitions are there: state equations and output equations. state equations. So state equations are n first order differential equations. N first order differential equations are called state equations. This is obviously in terms of state variables. And last one is the output equation. So this is algebraic equation relating output to state. So these are few definitions related to state space analysis. Now we will represent in general form of state space. How any system can be represented in a state space. So general state space representation is like this. We have two equations. One is x dot equals ax plus bu. This is called the state equation. And another is y equals cx plus du, which is called the output equation. So these are two equations, set of two equations, which is called general state space representation. So what are quantities in these equations? X is the state vector. Obviously this is a set of state variables. And this is the derivative of state vector. Obviously this is with respect to time. This is the derivative of state vector with respect to time. And u is the input vector and y is the output vector. So these are four quantities used in these two equations. Now we have another four quantities A, P, C and D. These are four matrices. This is called the system matrix. P is called the input matrix. C is called the output matrix. And D is called the feed forward matrix. So these two equations are very important. These are very important equations with respect to general state space representation. And obviously this is a vector. Vector means combination of variables. This is a set of variables. This involves many variables. And state variables are minimum set of variables in terms of which we can represent all variables. Suppose we are taking a network. So to represent the network, suppose we are taking loop currents. So minimum 3 loop currents, suppose for any system minimum 3 loop currents are required to represent all voltages and all currents through all branches and all elements. So this is state variable, means minimum set of variables required to represent completely any system. This is the derivative. Suppose we are using 3 variables, x1, x2 and x3. Then x dot means we have 3 derivatives also, x1, x2 and x3 dot with respect to time. Obviously this is the dx1 by dt, this is the dx2 by d2, dx2 by dt, and this is the dx3 by dt. So these are derivative of state vector with respect to time. And input vector, this involves many inputs. Suppose any system involves 2 inputs, then this this input vector contains 2 inputs. If we have 2 outputs, then y1 y2, this is, so all these are vectors. Vectors means set of variables. So this is all about the general representation. Now we will take an example. How can we represent in a state space? So now take an example. Example is represent in state space a system having 2 inputs u1 u2 comma 2 outputs y1 y2 and 3 states. These states are x1, x2, x3, and also represent system in matrix form. Matrix form. So matrix representation is also important. Matrix representation. State variable analysis involves matrix representation. So now this is the statement of problem. Represent a represent in a state space a system having 2 inputs u1 u2, 2 outputs y1 y2 and 3 states x1 x2 x3. So this is the question. Now we are starting solution of this problem. How can we represent? Obviously this system involves 3 states, means this is a third order system. So basic equations are, so now come to solution of this. Basic equations are this: x dot equals ax plus bu and y equals cx plus du. So these are 2 basic equations. How can we represent? So now we have 3 state equations: x1 dot, x2 dot and x3 dot. We have to write 3 equations for this first equation. Means first equation is a combination of 3 equations: x1 dot, x2 dot and x3 dot. So we can write like this: 1 1 x1, 1 2 x2 plus 1 3 x3 plus. So this is the first part. Ax means we have three states: x1, x2, x3. So this is the combination of three states plus inputs, two inputs. So we can involve two inputs like this: b11 u1 plus b12 u2. Similarly, for second, we can write a121. We can use suffix 21x1 plus 22x2 plus 23x3 plus for inputs b21u1, b22u2, and for third equations we have a31x1, a32x2 plus a33x3, and for inputs b31u1 plus b32u2. So this is a set of three equation is first equation, and in matrix form, how can we represent this in matrix form? So this is the state equation. This is called the state equation. In matrix form, if we write, then x1 dot, x2 dot, x3 dot, this is the column matrix in left hand side. Here system matrix A, this is formed by this three parts. So from here we can write first row of this matrix is formed by coefficient of x1, x2 and x3 from first equation, that is 1 1, 1 2, 1 3, and second row is formed by second equation 2 1, 2 2 and 2 3, and third row is formed by third equation 3 1, 3 2 and 3 3. And here this is the state x1, x2 and x3 plus for this part PU means this part is formed from these parts. So from first equation, coefficients of u1 and u2, this means first row 1 1, 1 2. From second equation 2 1, 2 2. From third equation 3 1, 3 2. So this is the matrix representation of this. So this is the half part of the problem. Means we are writing only first equation. Here x dot equals ax plus bu. So these three equations are called state equations, and in matrix form we can represent all these three equations. We can say this is the first part, second part and third part. These are three parts of first equation. In matrix form we can represent like this. So now next part, how can we represent output equations? So come to the second part, output equations. Output equations means this equation y equals cx plus du. You have to represent output in terms of the state variables and inputs. So outputs are, we have two outputs. So you have to write two equations, y1 and y2 for outputs. In terms of states means three states. In terms of inputs means two inputs. So you have to involve all three states and all two inputs. So three states. So we can like this: C11 x1 plus C12 x2 plus C13 x3 plus two inputs. We have two inputs, so you can write 1 u1, 1 u2. So this is the first output equation in terms of three states and two inputs. Similarly, for second output, you can write 21 x1, 22 x2 plus 23 x3, and two inputs means D21 u1 plus 22 u2. So these two equations are called output equations, which is this equation y equals cx plus d. And in matrix form, how can we represent this in matrix form? In matrix form, these two equations can be represented like this. You have two outputs, means a column matrix for left hand side, y1, y2, and from these two equations, first row is formed from coefficients of x1, x2 and x3, that is C11, C12, C13. Second row is formed from this second equation containing all coefficients of x1, x2 and x3, that is C21, C22 and C23. And states, three states x1, x2, x3, means x1, x2, x3 here as a column matrix, plus for input we have two equations. You have to form two rows. First row from first equation, that is 1 1 1 2, and second row from second equation, that is 2 1 2 2. So these are coefficients of u1 and u2. So this equation is the matrix representation of output equations. So this is all about your problem. So we have three states x1, x2 and x3. We have two inputs y1 and two inputs u1 and u2 and two outputs y1 and y2. So we can represent in a state space form, means we can represent this system in these two equation form, that is x dot equals ax plus bu and y equals cx plus du, like this. Obviously you have to involve all three states for derivatives of states, and you have to involve all three states for two outputs also, because we have three states, means these are three minimum required variables to represent completely a system, and you have to involve all inputs, that is u1 and u2. If you have three inputs, then obviously one element is more. So since we have only two inputs, then you have to involve two inputs, u1 and u2. Obviously choice of coefficient is free. We can use any other set of coefficients, means system matrix. And for input matrix, here we are using A11, 12, 13, 21, 22, 23, 31, 32, 33. Obviously this is for first equation, for second equation, for third equation. So this is all about state space representation. So this is the general state space representation in state variable form. So these are two basic equations. We have taken an example and represented in the state space. So in next term we will take some other examples, practical examples. How can we solve in state variable form? So okay, thank you. This is all about for today. Thank you.